Okay, so now we understand the approximation versus generalization relationship, and it's time to further understand the role of n, or the number of data points that we're using when we are looking at this approximation versus generalization trade-off. Okay, one quick example could be that let's say you have a preferred hypothesis set H. For example, let's say it's a neural network, right? So you're like really adamant in using a neural network for whatever problem you're trying to solve, right? Now, this hypothesis set, as we know now, comes with some complexity or a VC dimension, right? And that would be fixed for my hypothesis set, right? And once I've decided that, then this also comes, like this also leads actually to picking some n, like the number of data points, so that we can, let me write it down, picking some n that will help us at least achieve the very first rule of this. Why? Because these are like related to each other using an error bar, and we're going to discuss that now further. So basically, this process that we're talking about of that leads us to picking n is something that's known as sample complexity. So that's what we are looking at now. Sample complexity, and is defined as how many training examples n are needed to achieve a certain generalization performance. Right? So that's how we define it. How many training examples basically do you need? Now, if you remember the bound, the error bar specifically, it had n, right, as one of the parameters there, and it also has the VC dimension in there. Now, we can use the VC bound to estimate the sample complexity for a given learning model by fixing some delta and some epsilon. Okay, what am I talking about? Let me actually write it down, right? So the error tolerance that we've talked about earlier, epsilon, it determines the generalization error. It determines the generalization error. And we also have the delta. Like, remember, we used to say that we have this generalization error at most epsilon with probability at least 1 minus delta, right? So delta is essentially nothing, but it's determining the confidence with which this error tolerance is like exists, or when is it violated, right? So this is like a confidence value or a confidence parameter. And how are they related to one another? So epsilon would be, or like this could be a way of, this is a bound, of course, and saying that 8 over n log 4 to n dvc. Of course, I've ignored the 1 there because I'm just like trying to establish the relationship here, and delta, right? So as I said, we can fix a delta, and suppose we want the generalization error to be at most epsilon, then we can I would say solve this equation in order to get some value for n, right? So how do we do that? Let's go to the next slide and see what we are talking about. So this is sample complexity. How many n do we actually need for a given hypothesis set, essentially? So this is the error bar with the +1, of course, here. So this is the equation that I was talking about. And now I can rearrange terms and solve for n, right? The whole point of doing that is that I can actually get a relationship between n and the VC dimension. And as you can see that this relationship is this, approximately this, and this is linear, right? So this gives us some kind of an idea of the sample complexity, although you can see that n appears on both sides of the equation, right? Here, n appears here and here, right? And so what we can do is we can get some kind of an approximation by substituting values, or maybe get an iterative method to kind of solve for n, right? So let's look at this example to further understand what I'm trying to say. So the first and foremost thing, is that there is a linear relationship between the VC dimension and n, of course. And of course, n appears on both sides of the equation, so we cannot directly get that. Okay, so to obtain a numerical value for n, we will use a simple iterative method, and this example is showing us exactly that. Let us assume we are looking at a learning model with VC dimension 3, and for example, the 2D perceptron, right? How about a 2D perceptron that had VC dimension 3? And we have the error bar, or the error tolerance that we are allowing here in the learning process is 0.1, and the confidence value is 90%. So basically we are saying here that delta is 0.1, right? Because with probability 1 minus delta, we said that this like the confidence parameter delta essentially determined how often the error tolerance was violated. So that's exactly what we're doing here. Okay, so now the question arises, how big a data set do we need, right? And in order to do that, what we did was we substituted some values. So basically with n equals 1000, we kind of substituted all of that, and then we got a value of n around 21,000, approximately 21,000. And we continued this until we converged to some estimate of like 30,000 almost. So basically this is telling us that with a VC dimension of around 3, we need 30,000 data points. Similarly, we kept doing this iterative process, and for VC dimension 4, it seems we need 40,000, and for VC dimension 5, we need 50,000. Well, for those of you who have looked at like real world problems, who have worked with machine learning problems, you know that this is a gross overestimate. This is not what we need, right? In practice, this is not what we need, but this is what the theory at least is suggesting, right? And like, of course, there is like n is linearly related, or linearly, it's like approximately, I would say, proportional to the VC dimension, right? And so this constant of proportionality suggests that it's like 10,000 times like the VC dimension, right? And so based on our practical experience, based on our practice, and models that have been implemented, we come up with a practical rule of thumb, which tells us that n should be almost equal to 10 times the VC dimension of the hypothesis set that you're using. So basically, to summarize, in practice, what we like to target is 10 times VC dimension. This is considered like enough, sufficient. But if we have data of the order 100 times the VC dimension, then this is considered safe. And if we have data of the order 1000 times the VC dimension, then this is like the best case possible, right? So this is really what we would like to have, but then definitely 30,000, like of the order 10,000 essentially, is not what we want. So that's not the sample complexity that we require. Okay, so now we know how my sample complexity, how much data is sufficient for a certain given VC dimension, given some error tolerance and given my confidence parameter. And based on that, I can get an estimate of the number of points that I would require for my model implementation. Having said that, now we have to look at the generalization bound again and interpret it in terms of like the data that we have, and also in terms of like how loose the bound is, or whether like it's the generalization bound is useful or not. So